Hello everybody. Today we're going to work on finding probabilities and sampling distributions of the means. Let's get right to it. So what we have collected is data that is on Twitter users. And according to our data, Twitter users spend about 25 minutes, about average of 26 minutes, on Twitter, posting, reading posts, so on and so forth, with a standard deviation of 9 minutes. That's what our studies brought out. From here, I'm going to ask a few questions. First of all, what is the probability a random user spends less than 40 minutes posting? Good question. So over to my data, I know the mu is 26 minutes. I know the standard deviation, let me just verify that, is 9 minutes. All right, from here, part A. The first question is, what is the probability a random user spends less than 40 minutes? Well, because they say it's a random user, we're looking at one single person. That's very important to me. N is 1 in this case. It's a random single person. That's huge when we're doing sampling for the means. This is not a sample. We're looking at one person. So what do I know about the normal distribution? Well, 26 goes in the middle because the mean should go in the middle. The ones and the negative ones are all about the standard deviation. So if I add a 9 to the 26, I get a 35. And if I subtract off, what do we get there? 17? Because 17 plus 9 is 26. And so I get a kind of an idea of the spread of Twitter users and how long they spend on Twitter posting and reading files. So I want spending less than 40 minutes. Well, if I do another standard deviation, that would get us where? 44 minutes. Because all I did was add another 9 minutes. Every time you move on the normal plot, you are adding the standard deviation. That's why it's so important. Now, 40 is right here. That's where 40 minutes is. We want the probability somebody that posts is using less than 40 minutes. That would be the shaded area. How big is this? Well, that is our job to find out. The technique we used is the following. Part A, or step 1, draw a quick picture. Step 2, change your X value to a Z value. Well, the good news, in our previous video on normality, we talked about the transformation formula Z. This transforms an X value to a Z, all right? And that arrow is going the wrong direction. That arrow, that's an X value. And so it's going to be plugged into this formula. So our Z in this case will be 40 minus the mean for the problem, 26, divided by the standard deviation of 9. So in this problem, our Z value is 40 minus 26, and then divided by 9, which gives us 1.56 as our Z value. Once we have our Z value, it's your choice. Do you want to use Excel, or do you want to use the tables to find the area associated to the Z value? Because we have Excel, I'm just going to utilize Excel and do norm S dist of that Z value. And let's do that on our Excel file to see what the answers look like. So I'm going to have a couple variables in here, N, X, Z, and the norm S dist, which would give us the below, by the way. And we'll talk about that soon. N. Well, in this case, it's a random user, so N is 1. Our X, what value are we looking at? 40 minutes. The Z value. Well, by definition, the Z value will be X minus the mean, 26, divided by the standard deviation. See previous files on normality to see how this was developed, this transformation. So there's my Z value, as we've already gotten. Then we can either use the normal table or the norm S dist. Look at what the norm S dist is looking for. The Z value, good thing we got it, comma, cumulative. And again, we always choose 1 when we're looking at the norm S dist because we're always looking for area, and that area will be done by calculating an integral. When you put the 1 on, it turns on the integration ability. And so that is the area below, 94%. So going back to my picture, I know whether you look in the table or whether you use norm as dist, you're going to get 94%. I always like to pause to make sure this is the answer I'm looking for. Well, let's be careful again. Norm as dist is the area below the bar. This bar, the area below the bar, is 0.94. That lines up with the blue area, and that's important. A less than and a below is automatically given in the normal table or via norm as dist. So 3 and 4 are the same thing. The answer you're looking for is there's a 94% chance of this outcome. And that's really cool to know. Is given we have a normal distribution, I can utilize the average and standard deviation to build a profile of our Twitter users. And so if somebody says, what's the chances a person is going to spend 40 minutes or less on Twitter? The answer is 94%. Why would we care? Well, if we're putting in advertisements, if we're looking at stress on the computer system with the internet, there are many, many reasons we would like to know about Twitter usage, mainly for marketing for the most part. Excellent. Now, let's go back to the questions. Part B, what do you need to know about the time spent on Twitter to do part A? Well, I've already said it a few times. You need normal. And that's because if your sample size is small, unless you have normal, you do not have the right to draw the normal table. There is no right for you to draw the normal table. So you need normal, period. If you don't have normal, go prove to me it's normal. How do you prove normal? Well, somewhere must be the data for this, right? Somewhere must be the data for the Twitter. You have to look at the Twitter data and you prove to me that it is normal. How do you do that? Check out my video on checking normality, and you can see how to at least give an idea that it is normal, the data. All right. The only question I had to do with part B there is to make you understand you do need normal when you're looking at one user. All right. You can't just assume normal. All right. Part C. What is the probability the sample average of 28 users is less than 30 minutes? All right. So what we have is we have users now. We have a group of 28 coming in. So we have a group of 28 coming in. And so once again, I'm going to draw my picture, my normal picture. The standards are still true. The average is 26, and the standard deviation is 9. We now have a group, and that group is 28 users. Again, let me just verify that. Part C, 28 users. And we want to know when their average time, average would be X bar, sample average time is less than 30 minutes. So how can I build a picture? Because step one in all these questions is always to draw a quick picture. Here is the key when you're dealing with samples. And understand, this is a sample. You have 28 users. That is a sample. So what samples do is they change how I draw my picture. When I talk about the spacing here, this spacing, this error is no longer just sigma. It is an adjusted sigma based on the fact you're using a sample. It's called sigma X bar. Now, sigma X bar is just a formula. It's the standard deviation of a sample, better known as the standard error of the sample. What is it? It's the old standard deviation adjusted by the square root of the group size. So in our case, we would take 9 and divide it by the square root of 28. So 9 divided by the square root of 28, giving us 1.7. Notice the spacing. It's 1.7. So on this chart, I'm going to move by 1.7. So if 26 is the center, if I add 1.7, that would be 27.7. If I go again and add again another 1.7, where would we be there? That would be 29.4 if I've done my algebra correctly. All right. If you add another 1.7 onto 27.7, you're at 29.4. That's important because the bar I'm looking for is right there, 30. I want to know, in a sample of 28, what are the odds this group averages less than 30 minutes? So this amount of area. And I would not know that is such a large area unless I knew about samples. This is very important to me. Up here, we were dealing with one person. This is the spread of one person. 30 minutes is not that big of a deal from person to person. In fact, the typical range is 18, twice the standard deviation. So 17 to 35 minutes is a typical user. All right, that's the per person differential. There is 9 minutes, a wide span. But when you're talking about a group, this is the key idea with a group. When you're in a group, spacing gets tighter. Look at the spacing here. Just with a group of 28, I don't expect the difference to be per group more than 1.7 minutes. Okay, that's a 1.7 minute difference, and then another 1.7 minute difference. Why is that? You have to understand the idea of a group. In a group, the majority of the members of the group are going to use typical amounts of time. That means they're going to be spending their time around 26 minutes. And if the majority of the group is around 26 minutes, that means when you average, the average of the group is going to be tightly packed around 26 minutes. Hence, the spacing has to get smaller because you're in a group. And that's what this number represents, this fraction represents. It's the old spacing divided by the square root of n. Why the square root of n? Please go on to grad school to learn about that. For us, we just acknowledge it in our formulas, that in a sample distribution of the mean, you take the average as the center, because the average is the average no matter what. I don't care how many people you have in the group, the average will be the average. That's just the way it works for average. It is the standard error. The standard error of a group is adjusted by sigma over radical n. That's important, because when you translate in a group, you have to be very clear and conscious that you have a brand new formula when you're looking for the z-value transformation for a group. It is very similar to the classic one, but the denominator, that's really what I point out, the denominator has changed because you're in a group setting. I would pause, take a picture of this screen, and utilize this formula for what it is, for when you're dealing with a sampling distribution of the mean. How do you know you're dealing with a sample distribution of the mean? Well, come on. This question's about the mean, and you're looking at samples. That's why. So, we haven't even done the question yet. I've just set it up. This really is my step one. Building me a picture so I have an idea of my answer. See, if I just willy-nilly click 30 up here, the answer would be pretty small, just above 50%. That's not the true answer. If you're using this graph, that means you're looking at one person. We're not looking at one person. We're looking at a group of 28 randomly picked. Again, that really adjusts the spread factor. That's the key ingredient. So now, after we know that, now we go to the steps. So step 2, we pick the right Z formula. Well, the appropriate Z formula for a average, for a group, is x bar minus mu over the new standard deviation, sigma x bar. Well, x bar, what you're studying, is 30. The sample average you're studying is 30. The national average will always be the average. The national average was 26. The new spread factor is 1.7. This allows me to find a Z value. So I take my calculator. 30 minus 26 is 4. 4 divided by 1.7 gives me a whopping 2.35. Welcome back, everybody. There is a temporary glitch. And so we were working on this problem right here. Z equals 2.35. After you get a Z value, you should go to your norm as dis function, because that's what the norm as dis does. It takes a Z value and it wants you to find the probability. That is, when you plug the Z value into norm as dist, it'll find the probability. And it's very important, the norm as dist finds you the probability below. All right. So the norm S dist of this Z value, comma 1, you always should put a 1 there to turn on the integration, gives you 9907. Well, that is the area below. All right. The area below 30 is 99.07%. 99.07%. If you're curious about the area above, it would be 1 minus. This red region is a very small region, less than 1%. Because again, if the blue region, which norm S dist gives you, is 99.07, then the area above is 1%, or less than 1%. All right, so we just finished this problem. And of course, you could do this in Excel by typing in the formula. And you got to be careful when you type in the formula. Parentheses around everything needed, so pause and make sure it makes sense. X minus mean divided by the old sigma over the square root of n. And once you have that, that is your Z value, you can utilize norm S dist to get the area below. This would be the most accurate answer. If you don't want to do rounding, this would be the most accurate answer. And this is the answer to that question. Now, part D, what do we need to know about the timeline? Once again, we need normal. You see, here's the problem. 1 user, 28 users, you better know about the distribution. You better know about the distribution of 1 user. You better know about the distribution of samples of 28. That's very important here. This is about distribution of samples of 28. If you get to 120 users, we get a cool fact. That is, we get a fact for free. We know normal. We get normal for free because of central limit theorem. You see, the central limit theorem kicks in at 30. And what the central limit theorem says is, as long as your group is over 30, we know the samples are roughly normal. And that is awesome. That means as long as you sample over 30, you get normal for free and can always use the normality and the normal picture to answer any probability questions you have. If it's under 30 and you are stuck with under 30, like groups of 28, then you need to show me that groups of 28 are roughly normal. How do you do that? You collect data on groups of 28, and then you would watch my video on checking normality and check out the ways you could check for normality in sets. Same thing with a random user. But again, if you're over 30, you get normal for free. So let's see if we can attack this question. What is the probability the average of a group of 120 is less than 30? Well, the way I would answer that is just like the previous question. I'd write down the key ingredients. Average is 26, standard deviation is 9, n is 120, x bar is 30. What that leads to is my new spread factor, because your new standard error, your new spread factor in the picture will be the old standard deviation divided by the square root of n, which I calculated out to be very small. Please notice that. Wow, oh wow. Notice the spread factor. The spread factor up here was 1.7 minutes. The spread factor up here was 9 minutes. What's going on? That's the key ingredient to samples. When you don't have a sample, that is 1 person, the spread factor could be very large. But as you increase the group size, so you went to a group of 28, now the spread factor between groups is 1.7 minutes. Why is that? Because in groups, not much changes. Most of the group will head towards average. There'll be a few that use it high or use it low, but those average out. It's really the predominant members are average users, so the spacing gets smaller. And the larger the group, the more that's true. The larger the group, the more the spread factor comes down. And so when we are now at a group, where are we at? We're a group of 120, so then the spread factor is really small. In a group of 120, the majority of them, over 100 of them probably, are going to use right on top of 26 minutes, which means in averaging ideas, if the majority of people are on 26 minutes, then there's not much leeway to be moved, and there isn't. And that's really the big theme. So I'm going to use 0.82 as how I jump in this picture. I'm going to use 0.82 as I jump. So if I'm looking for 30, holy moly, 30 is way off the chart. And so the odds you're under 30 is very, very good, extremely good. How exactly? Well, use your Z formula, and you got to know you have a sample. How do you know you have a sample? Well, dude, it said we had 120 people. That's a sample. This is our sample formula. How do I know? I got my formula sheet. And if I have a sample for the mean, this is the formula I would use. All right, calculate my z-value. Wow, it's huge. And as soon as I knew the z-value was over 3, I knew we're in rare area. A 4.88 is something that should not happen. And if it does happen, I'm going to go, whoa, because a z of 4.88, so 30 minutes is way up here. A z of 4.88, which means the area below that is ridiculous. The area below a 4.88 is almost everything. Almost nobody lives above a 30 when it comes to average Twitter users in a group of 120. And in fact, I know that answer. It's 1 out of 10,000, 0.01%. 1 out of 10,000 groups. So if you find me a group of 120 and they're using it more than 30 minutes on average, something's happened. Either the old average is wrong or something big time happened on Twitter. Something huge happened so that this did occur, okay? Because there's a 99.99% chance that it's going to be below. All right, let's go to Excel and see how we did it. So with the N and the X, you can, again, find Z using the formula. X bar, I should say, because that's average. X bar minus mu divided by the new spread factor. And the new spread factor is N, or 9, divided by the square root of N, 30. Once we have Z, then we can go and find the probability underneath. And in fact, it's always fun to see, look how many 9s you get. Look at it, it's 99.99994% chance you're going to be below this number, which means being above this number is almost impossible. Now we wanted less than, so that's our answer. Guaranteed. Almost guaranteed. You're going to be below 30 minutes. So when I see a group of 120 users, I want to know their average and their chances of them averaging less than 30. Almost guaranteed. All right, next question, part F. Part F. The probability that the sample average of 48 users is more than 20 minutes. All right, let's do this in Excel. So we have 48 users, that's N. The cutoff is 20 minutes. How do I calculate out the z-value? Well, you calculate the z-value like you always would. It'd be the bar, X bar, minus the national mean divided by the old standard deviation over the square root of the sample size. And that's why I got negative 0.46. Please understand, we're on the other side of the spectrum down. We're on really below average. And that makes sense. 20 minutes is way below average when you're looking at group sizes of 48. So when I have 48 people come in, and if they last 20 minutes, I'm like, whoa, what the heck happened? That should not have happened. So maybe the internet went down. I don't know why, but I would study why the heck that happened. Because the chances of that happening or less is almost zero. Because again, e to the negative 06 is a very, very small number. So I know the odds, norm as dist, remember, is the area below. The odds of 20 minutes or less is extremely small. Now, this question was more than. So if I want more than, just remember, norm S dist gives you less than. In fact, binom dist, Poisson dist, whatever dist is always giving you less than in Excel. So if you want more than, you will do 1 minus, and that is actually our answer. The chances you're going to see a group of 48 use more than 20 minutes on average is almost guaranteed again. And that's because of the sample size. Please note the sample size is over 30, so I get normal for free. I don't even have to test and draw the histogram or box plots or find the descriptive box. I can just go right to answering this question. Because I have a sample size over 30, that is, I have a sample size of 48 users, I know I can use the normal distribution, and my answer is pretty darn sure this group of 48 is going to take more than 20 minutes on average. Notice, when it's groups, I'll talk about on average, because that's what you're doing. You're averaging out their user times. If it's one person, it's their exact time usage. If it's a group, it's average time usage. Average time usage. Very important distinction. Well, there are a bunch of type of questions you got to get used to. What is the probability is the first one. The next type is obviously the 8% cutoff, the top percent cutoff, and the bottom percent cutoff. Well, that is a different technique. Let's try this out. Top 8%, group of 36. So if I have top 8%, group of 36. First of all, group of 36 changes my spread factor. My spread factor is 1.5 units in a group of 36. That means 1.5 is the jumping mechanism in this group. 1.5 minutes is the jump mechanism. That's the spread per group. I think groups of 36 should have a potential difference of 1.5 minutes per group. That's what it is. Okay, top 8% would be a bar here. This is the top 8% of the users. Of course, top doesn't mean much in Excel or in the tables. So you'd look up the bottom 92%. Those are things you can look up. The bottom 92% in the table, or if you have bottom 92% and looking for a Z value, Excel has a function built for that. The norm S inverse says, you tell me the area below, I will give you the bar. And that's awesome. You tell me the area below, I will give you the bar. And doing norm S inverse gives me a Z value of 141. We can, of course, look this up also in the table. The table would be right here. The table, if we look up 141, is a 92.07%. That's really close to 92%. Again, 1.41, you could have looked it up in a table if you're a table friend, and you can see 1.41 is close enough to 92%. That would have been the Z value you could have utilized anyways if you liked the table. You just got to know what device you're using. If you're using the table, no, you're looking up 92% and you'd get 1.41. If you're using Excel, you got to know you're using norm S inverse. Norm S inverse again says, give me the area below and I'll get your Z value. We always have to use the technology and know how to use the technology. Once you have the Z value, think about this. Think about what you have in this formula. You have the Z value. You have the standard deviation of the sample or the standard error. You have the average. The only thing you don't have is X bar, but that's what I'm looking for. What is the sampling average that would put a group in the top 8%? That's what I'm looking for, that top left number. To solve, it's called good algebra. Cross multiply and add 26. Cross multiply and add 26. And that's how I got this number. I cross multiplied and add 26. So there's my bound. Bottom line, 28.12 minutes. If a group takes more than that on average, they'll be in the top 8% of group usage. And I'd wonder why they would fall in the top 8% if that's my threshold for looking at these groups. Of course, we could do this in Excel. You could, first of all, find, if I know it's the top 8%, I would use norm S inverse to find the Z by using 0.92. And then I would use the formula backwards. The formula backwards would be the mean, add on the new Z value, times the new spread factor. That times is that cross multiplying, right? Z times the new spread factor, standard deviation of the error. Plus add on the mean. The good news, this formula always works. So you can really import that formula in and have Excel do most of the work for you. So the answer here is, what group size do I need? 28 people. Sorry, what average time span? The group size is 36. In a group of 36, and so I should have wrote that there, in a group of 36, if they spend more than 28 minutes on average in the group on Twitter, they will be in the top 8%. That's very important. In a group of 36, if they're averaging more than 28 minutes on Twitter, they are in the top 8% of Twitter users. Excellent. All right, guys. I've done the first question. I want to pause now. I want you to try the second question. All right, so we're back at it. To answer these questions, you really should follow step by step, draw a picture, and go through the steps. I'm going to, because it's our second example, speed it up by utilizing Excel. So if somebody said, what is the probability of a random female is under 69 inches? Well, I need to know, is female height normal? It is? then that's awesome. I don't have to show anything as normal because I already know it's normal. That means all group size are welcome. Just do the analysis. Questions A and B, I'd really be worried about if I didn't have that normal distribution. A and B, I'd have to prove to you my data was normally distributed before I did these questions. Luckily, it says normally distributed, so I'm ready to roll. And so the mean is 64, the standard deviation is 4. Great numbers, so I can actually put them up here. Mean is 64, and the standard deviation is 4. This will help me as I write down each question. So what is the probability a random female? Very important. That's not a group. That's one person. One female is under 69 inches. All right, so my X would be 69. I need to change that to a Z value. That is on the standard chart. What is that? Well, when you're talking about a single individual file, it is X minus the mean divided by the standard deviation. And I did not divide that. Divide that by the standard deviation to get my new Z value, 1.5 units away. And that makes sense. If the mean is 63, if I'm adding 4, that'd be 67. If I'm adding 2, that'd be 69. So 1.5 does make sense in a single person picture. Now, I can utilize norm S-dist to find areas below a Z value. That's what norm S-dist does extremely well. It finds the area below. So I pause and make sure, was this an area below question? It was, and so there is my answer for part A. There's a 93% chance I'm going to find the next female I study will be under 5'9". That are the odds. And this is very important. We're looking at people buying clothes, people fitting into airplanes, people going on rides and roller coasters. Height is a very important thing we study when it deals with, again, roller coaster rides, airplane rides, leg room in cars. When we're looking at pant sizes, we're really trying to figure out, what are the odds of females under 5'9"? 93%. So there's not many females that are taller than 5'9". We're talking randomly, okay? That's very important. Randomly. If you're in a group of tall females, then you probably are tall. And that's not a random group. I want a random group. So I want to go to an area and randomly select one female. The odds of they're under 5'9" in a random female is pretty darn good. 93% chance. All right, part B. Why don't you pause and try part B now? So in part B, 16 is the sample size. I see the cutoff is 69 again. Z value. Well, I already know the Z value is going to be bigger because in groups, spreads get smaller, which means the Z value has to get bigger because the spread's going to be smaller here in this group. So what is the formula? Well, the formula is, again, the X bar you're looking for, and now it's X bar, average height. What is the chances we're going to find 16 females to average less than 5'9"? Well, it's 69 minus the center divided by the new spread factor. The new spread factor will be the standard deviation, and I did that wrong, parentheses or else I'd never get it right. The old spread factor divided by the square root of the sample size. That gives me a Z value of 6. And I realize, wow, I'm really off the charts. And the reason for this is because of this group size. This group size, when you take the square root of it, is 4. 4 divided by 4 is 1. So we're talking about a spread factor of 1. That means to go from a group here of 16 females to go from average to outliers is just 2 inches. So if I see an average group of 65 in a group of 16 females, it would be very outstanding because, again, let me insert something new here, right? The standard error. That's really what I'm working with here. I'm really working with this idea of standard error. The standard error, what is it? Well, the standard error is the denominator. It is the old standard deviation divided by the square root of the sample size. So in a group with 1, it's the same number. But with this group of 16, notice what happened. And of course, I got to be careful. In my formula, the D20 is the one that's staying the same forever. So I want to freeze it, absolute reference it. And I still screwed that up. How did I screw that up? It would be D20, which is, oh, no, there's your problem. D20 is not D20, huh? Is D19. There's your screw up point. There we go. Did I put D20 up there too? No, D19. We don't want the standard deviation to change in my formula, the numerator to change. The denominator, I want it to change by the end. Notice the standard error is only 1 inch now. In group size of 16, the standard error is 1 inch. So from one group of 16 to another group of 16 random females, the difference in average better be 1 inch. That's how tight they better be in height sizes in groups of 16. And that means if I want to see a group less than 69 inches on average, it's going to be sure, because the z-value is 6. Because if the z-value is 6, the odds of somebody being below a 6 on a z-scale is almost guaranteed. And in fact, Excel says, I give up. It's pretty much guaranteed. Now, is it guaranteed? No. But what you'd have to do is start adding zeros on until it finally flips. If you really want accuracy, there it is. There is your odds of seeing a group of 15 females and having them average size to be less than 69 inches or 5'9". It is almost guaranteed that's going to happen. Why, Dr. McCullum? Because the standard error, the spread size, groups do not change. So when we go to the next one, I got to get even more laughing because we're still at the same cutoff, but now we're at a larger group. You're trying to tell me you want me to find a group of 36 females and their average height is going to be less than 69? Yeah, guaranteed, because the spread factor in a group of 36 is under an inch. That means, again, when you take a group of 36 and another group of 36, two groups, their average differential is less than an inch in average height size. This is a very important phenomenon. When people say, hey, when I have a group of 36, why do I only have to sample one group? Why don't I have to do another group? Because the answer is, from one group to another group, things should not change that much, okay? So when you pick one good group, when you pick one good random representative group, the idea is that that group should really help you with the rest. All right, how do I find the z-value? Well, it is x bar minus the mean. And in fact, now that I have the standard error, the standard deviation done nicely, I don't have to rebuild a harder one. I could just utilize this one. And my z-value got even further out. That makes sense. The larger the group, the smaller the error, the larger the z, the higher the chances are that you're under that number. The chances somebody's under a z of 9, well, again, it's more digits than you see here. You might as well say it's 100% chance. It isn't. There is some weird infinitesimal chance you're above a 9. But your z-value of 9 tells me, woo, we got something really... Well, first of all, I'd worry you did the calculating wrong. If you didn't do the calculating wrong, something is really weird. At 6, something's really weird. So if you get a z of 9, this is really, really weird. Okay, let's do another question, like the bottom 4%. How would I do the bottom 4%? Well, first, I noticed the group size is 81. So the group size is 81. All right, the group size is 81. That tells me what my standard error is going to be. Pretty small. Notice, group size goes up. Standard error goes down. That just makes sense. It's called good algebra. Spread goes down. That is the important key element of today's lecture. As group size go up, error goes down. If error goes down, it is harder to get away, it's easier to get away from the center, but it's harder to me. That is, it is harder to move. It's harder to see movement in large group size. So, all right, what do we have here? The bottom 4%. That will tell me the z-value. Because with norm S inverse says, you tell me the probability below like 4%, because that's the bottom percent, right? Bottom percent is the area below. If you tell me the area below, I'll get you your Z value. So if you tell me the area below, so I should have put 0.04 here because that's the area below, then I'll tell you your Z value. Once you know your Z value, you can use the formula for Z transformation backwards. So think about this. You have the Z value, you have the standard error, and you have the mean. So if you take the mean and add on the standard error times the Z value, you get what you were looking for. The average that would be in the bottom 4%. So if I took a random group of 81 females, calculate out the average height of this group of females. If the average height was 62 inches, so 5'2", that would be in the bottom 4% of any group when it comes to height for female. And again, something worth studying. That's the idea, is once you know they're unusual, then you can ask, why is it unusual? First, you got to know it's unusual. How do you know it's unusual? Here is the analysis. First, it's a group of 81. Second, the cutoff is calculated by calculus. The cutoff is -175. All right, that's the cutoff. Why did I put 0.04 in here? Because norm S inverse looks for area below. In a bottom 4%, the area below is 4%. If it was top 4%, I would have used 96. But because it's below, I'm looking at bottom 4%. That's an important distinction. Now that I know the Z value, I can do the formula backwards, work the formula backwards, the transformation Z formula backwards, to find the sample average I'm looking for. So once again, if a sample group comes in of females, 81 females come in, and their average height is 5'2" and below, we have something unusual about height. And we're going to wonder what qualities about this group puts them in that height category. That is the lowest 4% for height. And that's the fun part. Why did they fall down there? I can tell you if they do fall down there, but why do they fall down there is your part. All right, guys, thank you for watching this video. Stay tuned for more.